My name is Justin Cohen. I'm a program manager with DARPA's Microsystems Technology Office, and I'm excited to share a vision with you for what I see as promising directions where optical microsystems can do more than miniaturize optical technologies. They can potentially do things that are impractical or even impossible for fiber and free space conventional optics technologies. These advantages come about from the way that we build optical microsystems. We're in the midst of a revolution in photonic integrated circuits, which can host thousands of interconnected optical components on a single chip. Augmenting these capabilities with PICs through other miniature optical components like high-quality discrete optical resonators or solid-state diode lasers, or even interfaces to atomic vapor resources and other resources like electronics for control and signal processing can provide yet more functionality. Building optical microsystems in this way leads to orders of magnitude in miniaturization for size, weight, and power, and to advantages in performance, a couple of examples of which are shown on the right here. Uh, through the past several years, integrated photonics has been on a dramatic scaling trend, shown by this chart, Moore's Law-like chart on the top right, showing that the latest integrated photonics chips are approaching millions of components operating in concert, and can generate new architectures that are completely impractical for scaling with fiber free space systems. On the bottom right, and being a bit tongue-in-cheek here, comparing hard drives to solid-state drives, but truly the move to monolithic photonic circuits with no moving parts can provide significant ruggedness and robustness advantages. We're pursuing these advantages through two current ongoing programs that I'm excited to be leading. On the Griffin program, we're using optical microsystems to generate ultra-low noise sources of radio frequency and microwave signals, where the unique combination of ultra-small, compact form factor and rugged tolerance to environmental constraints means that precision RF technologies can deploy to platforms that were never able to host them before. On the Inspired program that we just kicked off this summer, we're leaning into the high complexity of photonic integrated circuits, as well as the superior light-matter interactions and nonlinear effects that can be created in microscopic waveguides and devices to be able to create, manipulate, and detect nonlinear uh, quantum states of light known as squeezed light. In this case, using these special states of light to break the shot noise limit and operate at beyond the shot noise limit in sensitivity for optical sensing. And for the rest of the talk, I'm excited to share a couple of new directions for what I see as promising topics where other advantages can change the way that we approach new emerging technologies. Starting with quantum interconnects and networking. Interconnection and networking are central resources for information technologies. And for quantum information, this task requires distributing entanglement across a distance. And the experiments that can undertake this task today look like physics experiments in optics labs. What would it take to move from this picture to something that looks more like racks of quantum interconnects at the scales that power the global interconnect? Here's the complexity of quantum photonic circuits that could save the day, where thousands of channels can operate in concert to boost the rates of entanglement and make up for weaknesses in optical devices that lead to non-deterministic functions and boost fidelities. In addition to large-scale quantum photonic circuits, other advances that have been pursued for a long time in the microelectronics industry, such as advanced packaging techniques to combine multiple chips together, could provide yet another method of scaling by combining multiple chips as well as interfacing to advanced microelectronics for control and synchronization of multiple chips in parallel. And together, these opportunities allow us to dramatically scale the performance metrics relative to topics like quantum networking. If that's what complexity can provide, what about ruggedization? Here we're excited about opportunities in integrated ultrafast optics. Today, the mainstays of ultrafast optics are titanium sapphire-based lasers or fiber lasers based on rare earth ions. But these technologies require carefully environmentally controlled laboratories to operate. What if we could recreate these types of lasers with chip-scale integrated photonics, such as this image shown in the middle? If we can do this, this could mean deploying the advanced capabilities of ultrafast optics that are at the forefront of optical science and technology, and can and hold multiple world records in terms of microwave generation, time transfer, signal processing, and can even generate novel sources of light for attosecond science. Be able to scale and deploy these techniques to places that were never able to host them before. What else can we do with optical microsystems? Building in other types of physics with optical microsystems can open up yet more possibilities, whether it's quantum frequency conversion, using enhanced nonlinear interactions to translate between photons of diverse qubit systems to interconnect diverse and hybrid quantum systems, or entangled sensor networks to gang together multiple sensors to boost signal-to-noise ratio to regimes that are beyond what a single device could achieve. Or even looking at on-chip particle accelerators or high harmonic generation to create novel states of radiation like coherent X-rays or extreme UV light can open up new forefronts in optical science and pervasive capabilities beyond premier laboratories. Or even considering the ultra-low noise capabilities of chip-scale lasers, which are now rivaling some of the best lasers ever made, to do things like low-noise optical communication, which could open up new modalities of communications, potentially even through non-line of sight venues. So I invite you to consider these opportunities and to share your ideas for other advantages that can be pursued with optical microsystems. Thank you.